ठीक है. Good morning, student. Today I am going to deliver the last part of this very mega, I should say, Debye-Huckel equation, and I have already discussed the fundamental concepts of Debye-Huckel equation. Then I have already derived the Debye-Huckel equation, and in third part I had discussed the Debye-Huckel limiting law, and now this is the last and most important part, that is called Debye-Huckel Onsagar equation. And during my introductory part, I have already told you that it is directly related to that Debye-Huckel equation, but a great scientist, Onsagar, slightly modified that equation, and that is called Debye-Huckel Onsagar equation, or sometimes in abbreviated form DHO. And of course it is the part 4, but it is my humble request to all the students that in addition to all those equations, there are other parts also. So for example, there are several numerical problems related to Debye-Huckel theory. Then there are some deviations, because that Debye-Huckel equation is applicable for the strong electrolyte, but the condition is that is very, very dilute solution. So yes, there is some modification regarding that Debye-Huckel equation for appreciable concentration. Okay, so you will please go through all those additional part of that equation. Now, as you know that there are many books available in the literature related to electrochemistry and particularly that Debye-Huckel equation. But before preparing this lecture for you, I have gone through two important articles, and I request all the students that you must read these two articles. So you will have a very clear-cut idea about that Onsagar equation. Actually, when Onsagar actually discussed this problem, his age was only 22 years. Can you imagine? At the age of 22 years, when already Debye-Huckel already derived that great equation, Debye-Huckel equation for the strong electrolyte, one day Debye was sitting in his room, in his office at Zurich, as I have already discussed in my introductory part. It's a very good university, ETH University in Zurich, Switzerland. I have visited that Zurich University and other things. So he just entered that room and just said, "Professor Debye, your theory of strong electrolysis is incorrect." So you see that when he was awarded Nobel Prize in the year of 1968 for, of course, irreversible thermodynamics, during this lecture of this Onsagar, and it is of course available in the National Academy of Science, so complete biographical memories have been given in this paper, that how and what is the reason for this slight deviation and how he just modified that. So very interesting topic. So I have gone through this paper, and of course in 1968, although he has been awarded Nobel Prize for irreversible thermodynamics, but his contribution is in electrolyte solution is very, very significant, because that is the movement of the ions under the influence of the electric field. So therefore, this is the lecture of his Nobel lectures. And again, he started with that same thing, the motion of ions, principle and concept, and he has given the whole concept of that Arrhenius and Debye, Huckel and other things. And of course, that is also published in a very important journals, that is Science, the motion of ions and principle and concepts. So I have referred this to textbook, but because you are all student, M.Sc first semester students, so therefore, as for student, I have used these two books. I used two books. One book is Modern Electrochemistry, my most favorite book by Bockris and Reddy, first part. And for complete derivation, because you know that there are many books available in the library, but for the student, that an introduction to electrochemistry by Glaston. So I have followed this book for the complete derivation. Now, let me start with the things that this is the book, Bockris and Reddy, and you all know that Debye and Huckel, they actually derived that equation. And you know, I have already discussed so many times the concept of the ionic cloud, the central ion surrounded by the opposite ion, everything you know. But this modification or Debye-Huckel Onsagar equation, that Onsagar published these two papers. Therefore, generally we call that this theory was discussed in the year of 1927. And one of the most important point to be considered, that whenever you are talking about this ionic cloud or the ionic atmosphere, and there is a central ion, and you know that it is surrounded by other ions, so there is a movement, you all know. And during the Debye and Huckel, they thought that the movements are straight line type of the things. But first time he actually observed that the movements of the other ions follows the Brownian movement, zigzag Brownian movements. And there are so many factors, like you know that electrophoretic factors or electrophoretic forces, then relaxation force, I will discuss gradually, and then frictional force, the movement of the solvents and other things. So that is the slight modification proposed by that Onsagar. So first point is that Brownian motion must be considered. That is the first point. Second point is that you know that as per the Debye-Huckel theory, the concept is very simple, that there is a very symmetrical, spherical, symmetrical things is there, ionic clouds. And of course, there are certain different types of ions are surrounded by these things. But first time, according to Onsagar, if we applied some external electric field, these ionic cloud or that ionic atmosphere is disturbed or distracted. And what would be the effect due to this electric field? That will be studied by the Debye-Huckel Onsagar theory. And definitely, if there is electric field and there are different types of force, so that will directly affect the mobility of the ions. So naturally, the mobility of the ions is affected, you can call it. And how that is affected, that is called the simply Debye-Huckel Onsagar theory. Because after complete derivation, when I prove the validity of the Onsagar equation, I will show you some of the graphs. If I plot the equivalent conductance with the under root of concentration for univalent electrolyte like sodium chloride, or equivalent conductance and under root of C. So suppose this is sodium chloride, NaCl, then silver nitrate, like that, any types of things, KCl. And of course, because I am just referring the very old book, Modern Electrochemistry or the An Introduction to the Electrochemistry, therefore I am using the equivalent conductance, so don't worry for that. It is a unit, so if I take the gram equivalents per mole or gram moles, basically now people are talking about the molar conductance, the role of molar conductance and the concentration. That is the very important point. So it is a mathematical derivation, and it is called that extension of, I should not say that Debye theory, he actually insisted, and that Debye appreciated his approach and he agreed to work with him. So it is, you can call it is a extension of the Debye-Huckel theory, and it is a mathematical model that describes the ion-ion interactions. Then of course these ion-solvent interactions, because the movement of solvent is also there, and you know regarding the viscosity, frictional forces and other things. So that is also considered. So normal ion-solvent interaction, ion-ion interaction, relaxation time. I will show you some of the very simple pictures so you can understand the whole concept of, and it is not at all very difficult. It's not at all very difficult, I must tell you. So if you ask me, sir, what is the final formula of DHO or Onsagar equation, it is very easy to remember these things, because if you understand the Kallol's law, which you have already studied in your B.Sc classes, very simple thing, that the ionic conductance and ionic conductors are infinite dilution. That is very important, because the movement of the ions depends upon the concentration, is related to that constant, and there is a constant. So if you just remember this Debye, that Kallol's law, so you can very easily write this, the molar conductance at particular concentration, molar conductance at equivalent at infinite dilution, and in place of K, you just write is a constant A and B, which is very important. And this constant A and B will depends upon the solvent, very good, and the temperature. That's all. Because if we take water, A will be different. If we take ethanol, A will be different. If we take acetone, A will be different, because it is depends upon the dielectric constant, and you all know that because you understand the Debye-Huckel equation, the thickness of the ionic atmosphere, kappa is also very important. Valence is also important. These are all interrelated, nothing new things. And this is the actually values of A, 82.4 dt or half. Eta is the viscosity, coefficient of the viscosity is very important. And dt 3/2, like that. So now I am coming to that derivation part. Now, in the absence of external electric field, the distribution of counter ions around the central ion is spherically symmetric. Many times I discuss the same thing. I will not repeat these things. But when we applied some electric field, then of course there is a retardation, there is a distortion, and suppose I am using one anode and or one cathode, and suppose that positive ion is migrated towards these things. So there is naturally there is a disturbance. These are the normal positions. But it will take some time, because there is a, when it migrates that side, so there is a immediate falls of that surroundings. But fortunately, after it is a very fast step, that after some time again that so there is a new type of the ionic atmosphere. So one is old normal system, applied electric field, there is a distortion, and then it will regain its original position. So that time is very important, and that time is called the relaxation time. Very fast, 10 to the power minus 10 type of things. I'll show you that relaxation time and other things. Now, so therefore, whenever I derive these things, so I have to consider these three type of forces. In some books, it is written like the relaxation force, or sometimes it is called the relaxation effect or asymmetric effect, because distortion of that spherical symmetry, distortion. Number two, that if there is some solvent, so naturally, quite natural that solvents are also moving, and that will disturb these ions and other things. So that sometimes it is called the ion drift. And third is that frictional force. So I have to consider these three forces. So in one side, I will show you the picture, you can understand. In one side, we applied electric field, and there are three types of forces. So I have to balance these two forces. One is external potential gradient in one side, and another side asymmetric effect plus electrophoretic effect plus frictional force. So if I equate this equation, I will get the final equation. So let me show you the first point. My student, Mr. Abhishek has prepared these things, and it is available in the most of the books, in Indian books or any types of books, even in Bokris and Reddy. But they have not, their book is very current book, because they have given a ionic clouds type of things, ionic clouds type, thickness type of the thing. But it is the normal, spherically symmetric, normal things. And just quite natural, we applied some electric field. So you know that there is a movement of that. Definitely the central ion goes to that type of cathode. So spherically symmetric, distorted like that. But the most important thing, today I will not discuss the time of the relaxation, how you calculate that time of the relaxation, that is there, and definition of the time of the relaxation. And there is a formula that by that method you can calculate the actual time of the relaxation. Because you see that this is the normal system, therefore I have written it the old ionic atmosphere. You are very disciplined. Just I applied the external field, so there is a disturbance. But after some time, because once this migrates towards the cathode, so it is decreased. Even it falls to zero. And that can be calculated by this method. And Q, I also tell you that what is Q. It depends upon the Z valency of, suppose it is sodium chloride, so Z minus divided by Z plus. Then, of course, not only it depends upon the valency, as well as it depends upon the ionic conductance. If you see the Kohlraasch law, so lambda infinite can be calculated with the help of lambda of cationic species plus ionic conductance of the anionic species. So what I mean to say, that time of relaxation is very important, and it depends upon the types of the applied potential applied on the system. First old system, then there is a new system. So the time lag, it is not immediate process. So there is a time lag, and that is called the time of the relaxation. But but how do I calculate that relaxation force? So we need some Stokes law and other things. So first part is that is called the asymmetric effect. You can call it asymmetric effect or relaxation time. That is the first force which is responsible for that. What would be the second force? That is called electrophoretic force. So I am just showing you that diagram. Just coming over here, I took the help of Abhishek Katendra and prepared these things. So it is called the electrophoretic effect. You all know that when we will study the transport number and other things. Today I will not discuss the transport number and other things. You just think that it is called the electrophoretic effect, that means the movement of the solvent. And definitely this side is going to this side, but the solvents, they are all, that means the movement of the solvents also affect the movement of that ion. It will disturb that ion. So naturally there is a retardation things. And that force or effect is called the electrophoretic effects. And that can also be calculated with the help of Stokes' law. It is related to the viscosity, then radius and everything. So here what the Glaston, or even if you see this book of Hawkins and Reddy, so they have directly used all those formula, the three forces. And if you want to learn, every logic is there. That means you can understand the how do you calculate the relaxation time or the relaxation force or the electrophoretic forces. And then you have to add three forces and balance with that external applied potential. You will get the final equation. That is actually Debye Huckel Onsagar equation. So if you see this diagram, everything will be clear. As I have told my introduction part, that when we applied some voltage, so there are three retardation forces which disturb the symmetry. Okay? And that is exactly opposite thing is that driving force. That is called the externally applied field. So if it is A, suppose if it is A, and that is equal to three forces, if I write X plus Y plus Z. So one is, I have already told you, relaxation retarding forces, or you can call it the asymmetric effect. Second is that electrophoretic retardation, the solvent forces. And third is the frictional force. So I have taken this diagram from some internet, and I have also taken this diagram concept from this Bockris and Reddy. They have not given this plus and minus like that. They just considered is an ionic cloud, just a central ion, and everything is ionic cloud. Okay? And that is, they called it the ion drift. But in some books it is called the different forces. So therefore, these three diagrams are very important for complete derivation. The student must draw these three diagrams. And it is not at all difficult. I think in B.Sc classes also you have already studied the things. But in B.Sc classes, I think complete derivation is not there. That is the difference between your undergraduate level and the postgraduate level. Everything is very simple. So after this diagram, now I will derive these things. And derivation is very easy, that I have to write the formula of this electrophoretic effect, then frictional effect, as well as the relaxation effects. I have to sum all those forces and balance with that whatever the potential, applied voltage, charge, everything is there. So now the second part. First, I will write the relaxation forces. Same thing, sum of the relaxation force, electrophoretic force and frictional force. So now by one, I will write the final equation. I will not derive the individual part. So first, I will write the relaxation forces. It is given in any books. And of course, I consider the Brownian, I mean that Onsagar considered the Brownian motion. You have seen all these things. So that relaxation force is equal to, in some books it is like omega, or omega is a different thing, epsilon or simply E cube, Z, the valency. Now this kappa you all know, I have to use this kappa from Debye-Huckel equation. In this derivation I need to use that, the value of this kappa. And D, it is a dielectric constant. K is the Boltzmann constant and the temperature. And this is applied potential. Now this omega, or small w is omega, you see it is Z plus Z minus 2q 1 plus q half. Now this q, as I told you, this q, is Z plus, Z minus, Z plus, Z. And this is the ionic mobility, ionic conductance. So I will not go into details of that Q on the theta and other things. Directly you can write this relaxation force. Second is that electrophoretic effect. So electrophoretic effect or electrophoretic force, I have already told you it's based on the Stokes law. So it is Z, again this same kappa. Here is a new term is there. This kappa is different and this K is different. Capital K is different. Why I have written I, that means I, ion species and I, other things. So this is called the viscosity of the medium. Because if I take water, if I take ethanol, if I take acetone, naturally viscosity is different. And Ki is the, because we are using that Stokes law, coefficient of frictional resistance of the solvent. You know that if I take some glycerol, the viscosity is different. If I take water, it is different. You know, so that is always opposing to the solvent motion of the ions. And this is of course applied potential gradient. So you have to remember these things. Relaxation force, then electrophoretic, and the last is very simple, that is the frictional force. Again here is also Ki and mu I is the steady velocity. And if you ask me, sir, what is that frictional force? All the moving ions experience a resistance force by the medium, naturally. It is quite natural. If I take glycerol, naturally, it is very difficult for the ions per movement. If it is a water, so movement will be free. So that is the thing. So now I am getting three things. Now I have to plus, as I already told, X plus Y plus Z. So now, as I told you my first picture, that there is a externally this electric driving force, or sometimes it is called the electrostatic force, is depends on this externally applied field. It is counterbalanced by all these forces. So that part is there. Yes. An ion is moving with a velocity g under the influence of the electric field, and that is actually Z and B. We have to write the values of B. I will tell you 1 by 300 ESU, and you can remove this part. It is not necessary. But sometimes what happens, this is counterbalanced by that frictional force. It must be actually K subscript I, mu L subscript I. So I can write Ki is equal to, it is subscript I, like that. Next is very simple. As I told you, that it must be actually, there is some subscript, maybe some typographical mistake. You know, subscript. So frictional force, then asymmetric effect, and electrophoretic effect. It is counterbalanced by the external applied field, or it is called the driving force. Now, whole equation you divide by, for the mathematical simplicity, whole equation is divided by Ki and Vi. You just, so you can call it Ki Vi divided by K, like that. Here K cancel, but yeah, it's just a practice like that. So this part is also removed. Like that, here is also removed. Like that. And just if I rearranging this equation, that means if I take it out, mu I and V, this part, is equal to this. Ei Zi, it is minus, like that, also minus. You follow this point or not? Very simple part. I just rearrange this equation. So this. So I'll get this thing. Now the second part, it is just substitution. I have to substitute the value of this V. 1 by 300. So if I write is 1 by 300, so I have to multiply it with that 300. So these are all substitution. So potential gradient is 1 volt per centimeter, suppose we are, and one that is equal to 1 by 300 electrostatic unit. So if I write in place of V 1 by 300, so that means, so everywhere I have to mark 300, 300. Why I have just written like that? You just, because this part is common part. This part is also common part like that. So same thing. Now question is that, because suppose there are two terms. One is molar conductance, normal cases, and molar conductance at infinite dilution. And you have already seen these things, that you know the values of kappa and other things. 1 by kappa is the thickness of the ionic atmosphere. And if the solution is infinite dilute, the value of K is 0. Yes. And we have already seen that 300 Ki mu I is equal to Ez. So Ki can be written as epsilon z divided by, just all are replacement. So mu I is equal to Ezi 300 Ki. Actually, all everywhere there is some problem. So if I substitute these things, what I will get? Now, one thing is very important here. There is a system, because if we are talking about this infinite dilution, there is a question of degree of dissociation. If you take the weak electrolyte, you know that degree of dissociation will increase. But in normal strong electrolyte, most of the time it is right 1. And there is a relationship between this is, you all know, there is the Kohlraasch law, just ionic mobility or conductance, this and this. And there is a relationship between this mobility and this conductance. If it is a cation, so it is related to movement of the mobility of that cation. If it is a negative ion, so it is related to mobility of the anion. And of course, it is related to that Faraday. So if I apply this same thing here, so I can calculate this value of mu, or simply you can write also u also, alpha f. Actually, I should write this before that equation, because what I did, that I replaced this ui, because this ui, there is a relationship between the speed and the ionic conductance. Speed and the ionic conductance. So I have written here in this side. That is that equation actually. You see, that equation. So mu is equal to this divided by f. But of course, there is no role of alpha, because for complete dissociation, for the strong electrolyte, alpha is equal to 1. But you have to first write this thing first. So ionic conductance, this f, this same thing. Or I can write like that, divided by f. So multiplied by f. So alpha is already 1. This, because I am using f everywhere. So I am getting this final equation. equivalent conductance of any concentration is the product of mobility of the ion and Faraday constant and degree of dissociation. Now you have to substitute all those values. But again there is a problem of this thickness of the ionic kappa value. For that, because this is a constant value, 9650. Boltzmann constant, you know, absolute temperature, you know, variable is dielectric constant. W is again depends upon the types of the electrolytes. Basically, they have used the univalent electrolyte for simplicity and other things. So, again, I am just going to that back side where this is the value of the kappa. I think you remember these things. 4 pi epsilon square under root ni zi square half, complete half, actually complete half. dkt, same thing. And during the Debye-Huckel limiting law also we derived these things, applying this value of Boltzmann constant, applying the value of Avogadro number, electric charge. Bear in mind that because I am following that Samuel Glaston book, most of the values I have taken from the Glaston, so therefore you will be surprised that nowadays nobody is using the CGS unit. Everybody is using the MKS unit. But because my value of A and B and other things based on that Glaston, so therefore I am using these old values in CGS unit. So therefore I am using CGS unit. So if I replace all these values, that is, you know, all these things. So using all those values, we'll get, this is not T actually, this is I. Ionic conductance. Not T, slight mistake. I. So 29.15 Zi, Z you cannot change. Viscosity depends upon the types of the solvent. Dielectric constant temperature. Dielectric constant temperature. Again there is a problem, I think it should be 3/2. Some printing mistake. Now if I just replace these things, molar conductance. At normal cases, molar conductance at infinite dilution. And if I take univalent, so in place of Ji, because that is for the I species, but here it is cation and anion, so sodium chloride, so this part. Same thing here is also. But univalent electrolyte, that you know that Z plus can be equivalent to Z negative. So again, more simplification. So I will get Y from 29.1, how we convert it into 82.4, because there is a values of the omega, which is I think 0.505 like that. And there is a formula, how do you calculate the omega, or directly you can write this 2 under root of 2. So that omega value is actually 0.5 like that. So then the formula will be, final formula is that. Again same thing, here of course it is equivalent conductance in the book of Glaston, but in most of the other standard books it is actually molar conductance. Molar conductance in the infinite dilutions. Or you can directly, if you are confusing so many types of values and other things, so you can directly write to the 82.4, is standard value, dt, t, and viscosity is different. and 8.20 10 to the power 5, and this is, in Z plus Z1 is 1 for uni, and that is one of the demerits of that Debye-Huckel-Onsagar theory, that when you take the uni-bivalent or bivalent electrolytes, there will be change in the formula. But this whole derivation is a very old derivation, derived in long back 1927, is based on univalent electrolytes. So therefore, this data is only based on that univalent, and therefore when we validate the Onsagar equation, we means that they have taken sodium chloride, potassium chloride, silver nitrate, and hydrochloric acid, like that. Any books you will find all these things. So directly you can write all these things. There is no integration or differentiation. Only thing is that substitution of the values. I'll show you after this class some from the literature. So same thing in place of, because it is very difficult for any scientist or the student to cram all those things, whether it is 82.4, 8.2, because they have derived this on the basis of these values. So it is better, because for a common language, so don't worry about this A or these values, it is better to write A or B. That is very simple. So therefore, they have modified these things. 0 molar conductance A plus B, lambda 0 m under root of C, and you can write like that 82.4, 8.2 10 to the power 5. Now I am just taking these values from that page number 90 of that book of Glaston. So if it is water, dielectric constant is 78.8 or 80, and temperature is 25 degrees centigrade. So the value of A is 60.2 and B is 0.2. So it is a quantitative mathematical model. If you, in one sentence, if you know the formula of the electrophoretic force, if you know the formula of the relaxation force and frictional force, and it is equated with that applied electric potential, and substitute all these values, and if you know the exact potential gradient is 300 volt, so you can get some numerical values. So therefore sometimes it is called as a quantitative model, a general, and it is a slight modification of that great Debye-Huckel theory proposed by the Onsagar. Suddenly he thought that no, there must be some deviation, there must be some problem, and he went to Zurich and discussed with that Debye and his assistant Huckel, and he agreed. Then he modified this theory. So therefore it is called the Debye-Huckel-Onsagar equation. Basically Debye-Huckel limiting law is very important, Debye-Huckel theory is also important, but it is one type of mathematical model. Just substitution of the values, no differentiation, no integration, nothing, no simple algebra, just substitution of all those values of the mobility, ionic conductance, valency, electric charge, Avogadro number, Faraday and other things. So these things. Now the last part, again if I just test the validity, I have already done in the first part, again C and this for equivalent conductance, maybe 120 like that. Don't worry about the unit and other things. And again I am taking this from the cluster. How we prove that this system is good? Because when they plot this or equivalent conductance or molar conductance, I think you follow this point. If it is the old system, so number of gram equivalent, and if it is in modern terminology, number of gram moles, so molar conductance. If you see the Atkins or even Levine, some numerical problems, you will always find the molar conductance. At infinite dilution, molar conductance normal size. So they have taken, and a very good straight line has been observed. If you suppose NaCl. Of course, values are different than silver nitrate. These values is, you can cut it here, because the values of equivalent conductance are very high for the potassium chloride. ACl also is there. And for even in some books, strong electrolyte, ACl is also there, very high. So, in a nutshell, today I am giving the last part of this Debye-Huckel equation, that is the Debye-Huckel-Onsagar equation. And let me summarize all the things, because I have taken 4 classes for just to complete this Debye-Huckel whole electrochemical concept. And I hope that all these, at least fundamentals, now you can understand this: what is Debye-Huckel limiting law, what is Debye-Huckel theory, what is Debye-Huckel-Onsagar equation. And then, of course, as I told you many times, that there are large number of numerical problems which is based on the Debye-Huckel limiting law. How to calculate the activity of sodium chloride, how to calculate the activity coefficients. So you please do, if time permits, I will try to solve all those type of numerical problems, but there are many numerical problems. So you must, and the numerical problems are very simple. If you know mean ionic activity coefficient, you can also calculate. If you know the ionic strength, the calculation of the ionic strength is very important. And above all, you just go to the library, and this is book, as I told you, it is also I am taking from the library. There are 2 editions, and many books are available in the Bokris and Reddy, and also I told you that Roger Philip is also there, and D.R. Crow book is also there. I have taken, so please refer all those books. Thank you very much.